Any questions?
So this is pertaining with the ball rolling down a ramp. So if there was no friction, would we still use the rolling friction, the rolling kinetic equals 1/2 moment of inertia work squared? Because it's just going this way, right?
That would just be the same as box on ramp.
So it's just 1/2 mv squared.
Yeah.
And then can you explain the force diagram again? Why there's no non-conservative work? Because you started out about like the normal force and the friction are perpendicular to each other, so they cancel each other out. But I thought we only said forces and displacements are the only one that can cancel each other out for work.
All right, so in the case of something that is rolling, I guess we'll use the wheel. We're assuming an ideal roll, that the static friction is perfect, the surfaces have only basically one point of contact or one line of contact. So I have a normal force and friction acting at this point right here. The static friction is acting that way because if without friction it would be just sliding like that.
Yeah.
So friction is acting this way on the wheel. And well, actually, in both cases, it's acting at that particular point there.
Just
at one point.
okay.
If it's a perfect sphere in our perfect, nice, ideal situation, acts at one point. If it's a cylinder, it acts along the line.
Okay.
The same principle holds. But it's only acting on it while there's contact there. As soon as it moves just a little bit, it's no longer in contact. So friction is not acting at that point anymore, and normal force isn't acting at that point. So in essence, the displacement is so close to zero that no work is being done.
Because it went out of contact for that point.
Yeah, and so now it's on to the next point, which is only in contact for very, very briefly as it moves.
Okay. Because I was under the impression that when it's just moving, the normal force just stays constant, just like straight, and then friction just stays on that point across the whole ball rolling. So I know the normal force will cancel out the displacement because they're perpendicular. The only one I'm really confused about is the friction because they're anti-parallel. And when you said like it's just acting at one point and then it starts going back, but the point is still in there, but it's just in a new location for the ball.
Right.
But that would still be zero.
Yeah. Because the force acting on that point disappears so quickly.
I somewhat get it. I don't know what to ask though. So when we're thinking about non-conservative work, we have to imagine it at one point, and then when it starts moving, we have to see like it's following. So hold on.
If I was looking at that one point with
Yeah.
a normal force right there,
Mm-hmm.
I mean, I was trying to think of a different way that it would still end up being zero, but it's hard to do it that way because if I'm looking at that point right there, there's no normal force acting on it right now.
Yeah.
So normal force can't be doing any work on this point.
Uh-huh.
The only time you can do any work on that point is at that moment right there.
Yeah.
But, again, a split second later,
It's
that normal
not-
force is zero.
Yeah.
Same with friction.
Let me rationalize this in my head real quick.
Okay.
So what was it that?
Hey, Luis, you want to hang out? Just
Sure.
Luis, everyone.
Morning.
The weight is always just so for the weight acting on the ball rolling, is it also moving with the circle? or is it just staying in one point? Because
The weight?
yeah,
We treat the weight as if it's acting at the center, basically the center of the rolling object.
yeah.
Acting down the entire time.
Mm-hmm.
So some component of the weight is always in the direct, because everything has a gravitational pull acting on it.
Yeah.
And so work is being done by that.
So the normal force is acting on the bottom of the wheel
And the
But
top
the-
of the wheel.
and the top of the wheel, but since that it's moving, normal force disappears at that point. But since that the weight is acting on the center and is always pointing down, since that the circle itself is just the one moving, not the center of mass.
Yeah, that's a summation of the way you look at it.
Okay, that makes sense.
I mean, in theory, every single part of it has a weight acting down.
Mm-hmm.
It just, we generally add them all up and say, oh, it's acting at the center.
Yeah, I just watched all the videos and started putting timestamps on all of my questions, and then, like I did a whole marathon yesterday. I heard myself talk the whole time, but another question is when we're doing the ball on ramp again, we said it was spinning on the new point based on the parallel axis theorem, but when you let the ball roll and then it falls down from the ramp, just like let's say there's a ball rolling over there and it just falls to the ground, it doesn't spin on the new axis like that, it spins on itself on the center, right? Because that's how I visualize the parallel axis theorem.
You mean when it, sorry, you made us out, is it falling off the ramp or staying on the ramp the whole time?
It's rolling down a ramp and then it falls to the ground. So after the ramp, it's
So
just
after the ramp, then it has some spin to it.
yeah,
We're ignoring air resistance.
yeah,
So that spin stays constant as it falls.
uh-huh. But what I'm wondering is when we did the parallel axis theorem, we basically moved the center of rotation from the center of the mass to the point of contact of the
Right.
ramp. But the parallel axis theorem also states that when you move the center of rotation, instead of going this way, it's going this way around the new point. So it's
Right.
like this. But when a ball rolls down and then it falls to the ground, it doesn't roll like this. It rolls like this. So is there just like a sudden change of
Of the axis of rotation?
yeah, from the ramp and on the ground, but it's off the ramp? Because that's what
I
I'm
would say, yeah. That, what I'm trying to picture is it goes off the edge here. See how long it is before I stab myself with that. So
Yeah.
it's coming along, we have a actual point of rotation
rotation.
here.
Yeah,
That's constantly moving.
yeah,
And then it's still at that point right there
yeah.
until it falls.
Uh-huh.
Then it's gonna spin at a constant rate because the axis of rotation is immediately shift to here. Let's see, or is there some more abstract way of looking at that?
Because I understand that we derive the IW squared plus 1/2 mv squared because one is rotating, so we need the rolling kinetic, and then it's moving, so kinetic energy. But I get that whole part, but I just don't get like why did we shift the axis of rotation from the center to the end, to the point of contact of the ramp and the ball.
Because while it's in contact, that really is the axis of rotation right there. We can treat it as we have an axis of rotation here and the thing is moving with some, so we have, you know, the speed of the center of mass and then the angular speed about the center. But that comes as a result of, this is actually the point of contact, this is the actual axis of rotation. That if I do want that one better, sorry. All right, so there's my center of mass right there. With this being the axis of rotation, let's think in terms of torque.
Yeah.
We have the normal force that way, we have friction that way. Neither of them exert any torque about that spot.
Mm-hmm.
The only thing exerting torque is the weight, which is acting down there.
Yeah.
I do have a moment up there. So, since it is rolling because of that, this really, if this were the axis of rotation, the weight would not be causing would not be causing it to roll at all.
Mhm.
And as I say these things, I'm thinking, yeah, but you can, let's just keep it simple.
Yeah, please.
So, because the weight is not over the center of mass, it is creating a torque which causes it to roll, because that is the axis of rotation,
Yeah.
which ultimately leads to the fact that parallel axis theorem, which allows us to look at it alternatively as this thing is spinning about the center and the center is moving down that way. But really, if we started with Newton's laws to do this, we would look at the torque acting about that point right there. I think I'm repeating myself and missing your question.
Somewhat, but hold on, let me change topic real quick. So since that we said that the new axis of rotation is touching the ground and within the circle, so when we're solving for torque, we just have to, the moment arm is going to be from the axis of rotation, and then it's going to be the weight.
Yeah, so we would treat it, if we learn to do it that way, we would treat the axis, the moment arm to be a vector, basically pointing that way.
Okay.
So that would be R, F, and so the torque. But when you do a cross product, since you're multiplying perpendicular parts, I can treat it as the magnitude is the weight times that distance right there.
And is that going to be, and is the K height going to be towards the room for the R and F over
Yeah.
there?
Because R is that way, F is that way. R cross F, R to F
Yeah.
points outwards.
How do you determine that it's R cross F and not F cross R?
Because the powers that be define torque that way.
Also,
That's the formula.
it's just so it's R times F, so you have to start with R regardless of,
Yeah.
yeah.
I would say that it ultimately comes down to, in a right-handed coordinate system, it'd be R cross F.
Mhm.
In a left-handed coordinate system, I guess F cross R would make more sense.
Also, so the technique that you're talking to us about, right hand rule where it has to be the shortest distance from R to F,
Yeah.
it only works for a tail to tail method, right? Because
Yes, when they're tail to
okay,
tail.
because that's the one that's why I keep getting it wrong when we're doing the right hand rule, because I kept going head when we're doing like the lateral, the vector was going down, and then the normal force was acting up, but I kept trying to move it from.
Yeah, it's gotta be tail to tail.
Okay. What? Hold on. There you go. If you have a K, you have a vector, and then you have a K going this way, how would you cross K cross I? Is that even
Alright, so
possible?
If I have, let's say, I hat this way, J hat that way, and K coming out at us,
Mm-hmm.
then K cross I, is that what you
K
said?
cross I, is that even possible?
K's going out that way,
Yeah.
I's over there, fingers curled towards it,
Oh. Okay.
so.
So if it's a
Okay.
if it's a negative K, it would be
Negative K into the board,
yeah.
I is that way, so I have to put my hand this way.
Okay. Got it.
Thumb points down, negative J.
All right.
Bringing back good memories.
I wish it was. Unfortunately.
For angular momentum, can we use the same rules as that we followed with regular momentum when we have an inelastic, perfectly elastic, well, imperfect, perfectly elastic, perfectly inelastic? Can we use the same rules such as the conservation of potential of kinetic energy? We like.
Yeah, I suspect you can,
You never asked that question before?
well, it's tough enough dealing with just two objects colliding now to bring in the fact that it's rotating as it collides.
Okay.
Because as it hits, it would cause the other one to spin because of friction.
Mm-hmm.
That was the normal force if it's straight on. So angular momentum should be conserved. Yeah, I think the same rules would apply. I just haven't applied them.
Okay. Hold on, let me look for my other question. If there was no slipping, so no kinetic friction, would the ball still roll, or does the ball only roll when there's kinetic friction involved?
It's gonna roll if there is friction involved.
So regardless if it's static or kinetic.
Right, if it's static friction, then we don't have the sliding, we're gonna have the loss of energy. If it's kinetic friction, then there is some sliding going on,
So we lost energy.
and so you're gonna lose some energy.
Okay.
I think, going back to the other question about the bringing in the perfectly elastic
Angular.
rotational collision.
Yeah.
So if we want to talk real life, and I think this is probably why I haven't really considered it, is that you really only truly get perfectly elastic collisions when you're dealing with particle physics, when you've got tiny little particles where friction doesn't make any sense because you don't really have particles rubbing against each other.
Yeah.
So in that case, do you really have particles that at that level that are rotating as they hit? Because in my dissertation, I was just dealing with straight on
Mm-hmm.
conservation of kinetic energy,
Yeah.
using 1/2 squared, conservation of momentum.
Mm-hmm.
Was not worrying about any rotation that was going on.
Yeah.
So I think that's why I generally ignore that. I'll subject the next group to it.
I'm so sorry for them.
Yeah, I'll make sure you get credit then.
Oh, please don't put my name in there. I'm gonna get hunted down.
All right.
Wait, just one more question.
Yeah,
I will listen.
yeah, that's fine.
So, the ball rolling down again. You said the ball doesn't roll down in a way it goes this way. You said it goes this way if you put a light in it.
Yeah,
But how?
all right, so there's a split in here somewhere. Where's the split? There it is. The split is there. Okay, as it rolls, that split is still moving to the right.
Yes.
Why don't I start it closer? So the split is still moving to the right. It touches down, it lifts back up. At no point does it actually backtrack.
But doesn't it go this way? Because you said it's
If there's no slipping,
if there's no slipping.
so it's a perfect roll, then it's only gonna go in one direction.
Okay.
So, where am I? So there's the split in it. And so my finger's on it.
Okay.
My finger doesn't shoot back at it anymore. Now, if there is slipping, if it's moving forward, but there's some kinetic going on there, then there will be some backtracking. How much reality do you want to throw into a problem?
You know what? Let's go full realistic.
Full realistic?
I mean, like, but can you explain like an easy term? Because because when I still look at it, I follow with my hand. It looks like this light is going back, but you say it's not going back. So what my understanding of that is, when it goes down, the slit goes up again. But if I follow my hand on the slit, it goes down and then it goes back up again.
All right, so why?
You want me to draw what I'm saying?
Yeah, no, I think I have a good idea what you're saying.
Okay.
Wherever I put it. So as this rolls, are you seeing this move backwards?
Yes. Wait. It's just going down.
Yeah, but did it move backwards at any point?
No.
Yeah, so
Oh.
now, if it were slipping along here, then there's gonna be at some point in which it is moving backwards.
Okay. And then that's the reasoning that we use to remove friction and normal force from the ball rolling down the ramp. I think that's the reasoning why.
I think it all fits together. I'll say yes.
Okay.
All right, other questions? Riley?
I have a couple questions. So if you have moment of inertias for like a couple objects that are connected to each other,
Right.
how do you find the total moment of inertia for
All right, if you recall, the moment of inertia ultimately is the sum of all the MIRI squares. It's just a sum. So if I've got a pendulum here, rotating about this point right here, I can treat it as I've got a bar and I've got a disc, and I do them separately.
Okay.
Because this is not the center of mass of the bar, I would use parallel axis theorem. So I can do the bar about its center, add this bit in because it's not about the center, and then this one, obviously not about the center, it's rotating about that. So I would just do each part separately and then add them.
Okay, alright. And also, do you mind doing like an example of, like finding angular acceleration of just like a disk rotating?
As in an object rolling or like a pulley?
Like a pulley.
Okay. Let's see, we've done the Atwood's machine thing, so let's